So now we're going to talk about how to compute likelihoods directly. So here's this confusing formula here. We say the likelihood of our set of parameters, which is capital B, given our data, which is capital X, is equal to the product of the probability of observing the first observation given the parameters times the second observation all the way up to the nth observation. So it's the product of all of the individual probabilities given the parameters is the likelihood of the parameters given the data. So for example, in a Bernoulli process, the set of parameters is there's just one variable. It's the probability of heads. And so the probability of observing something is P if that thing is a success, and 1 minus P otherwise. Normally distributed variables, there's two parameters. There's a mean and a standard error, a deviation. And so we'd say the probability of observing a specific value given the mean and standard deviation comes from this formula in Excel, norm.dist. And then you have the mean, argument, mean, the observation, the mean, the standard deviation, and false, saying we don't want the cumulative one. Likewise, if we were looking to compute the likelihood of a chi-squared distributed variable, in order to calculate this individual thing for each observation, we'd say, oh, that's a mistake. Here, let's just pause that then. Go back. It is likelihood. It's not M and S, right? That's from the normally it's probably D. There we go. So chi-square distribution is a little confusing because the parameter is called the degrees of freedom because it has to do with the sample size. So the probability of observing a particular value in a chi-square distribution of this many degrees of freedom is chi-square.dist, value, the degrees of freedom, and false. So the same pattern in both of these. You have the name of the distribution, the word, then dist, saying it's a distribution, then the observed value, and then a series of arguments that correspond to the parameters that are being used to compute the likelihood, and then false to say that we want the probability density function and not the cumulative density function. So let's look at how this would work if we were computing the likelihood of a model where we were estimating the probability of heads. So flipping a coin is a Bernoulli process, and usually we count heads as success, and the one parameter is P, which is the probability of heads. And so to look at different models, we could compute the likelihood that the probability of heads is 0, that P is 0 given a data with 4 heads is 0. That's probably observing this given the model, times 0, times 0, times 0, 0 to the fourth is equals to 0. A fair coin means that P is equal to 0.5. The likelihood of this model, given 4 heads in a row, is 1/2 times itself 4 times of 1/16. And the likelihood of this model, given 4 heads in a row, is 1. So this is going to be, that's as likely as you can get. So the maximum likelihood here with 4 heads is that the coin is actually a trick coin with only 2 heads. Now notice, so there's an important thing here. That likelihood doesn't tell us which one's actually right. It just tells us which one's the best guess. And it doesn't tell us how much better it is than either of those. So how would we set this up in Excel? Well, if we had a Bernoulli model, you have the different outcomes here. And then you have an if-then statement here to compute the probability. So if the observation here is equal to heads, then you cough up the probability of success. Otherwise, it's this 1 minus thing. So you look up these two things, you fill that down, and that's going to be all your probabilities. And then the likelihood is the product of all of those multiplied together. And the log likelihood is the logarithm of this value. So we can use a similar setup for computing likelihoods of a Gaussian model. So once again, we have our data here. We have our computation for the probability of observing that particular piece of data given our parameters. The parameters over here. So we look up our parameters, say false. So we've got all each of the individual probabilities here, we multiply them all together and take the logarithm, and there's the likelihood of a Gaussian model. And finally, for chi-squared, our single parameter is the degrees of freedom. So we have observations. We have chi-squared distribution of this observation given this parameter. And again, we want the probability density. And so it gives us these numbers, multiply them all together, and take the log to get the log likelihood. So that's how we would compute it.